Alright, hello everyone. So in today's video we plan to prove the Riemann Lebesgue Lemma along with some other properties of trigonometric sums. So this is part of a course on Fourier Analysis, and this is lecture 2. Before we go ahead and continue, let me quickly remind you of what happened in lecture 1, or of some of the things. We defined the following stuff. So if we start with two periodic functions, 2 pi periodic functions, meaning they repeat every 2 pi, then if we also assume they're Riemann integrable, like we can integrate them, in particular they're bounded on minus pi pi, then we define the inner product of f and g to be this integral, where we integrate f times the complex conjugate of g over minus pi pi and normalize by 2 pi. And then based on this, we defined the Fourier coefficients. So these are the coefficients at n. And they're defined as such, like you integrate f against the kernel e to the minus I and x, and you integrate between minus pi and pi, and again you normalize by 1 over 2 pi. In other words, you inner product these two functions. And lastly, based on this definition as well, we may introduce a norm, and that's going to be defined as the square root of the inner product of the function with itself. In other words, we define the L2 norm of a function f to be like you take that integral, the inner product, so you put f here, and that becomes absolute value squared dx, and then you square root the whole thing. Okay, so this is the L2 norm of the function. So our plan for today is to introduce the notion, or to actually prove a fact about so-called best approximants. Like we mentioned in the previous video, that we're interested in representing functions that are 2 pi periodic as a sum of the form the nth Fourier coefficient multiplied by e to the I and x as n runs from minus infinity to infinity. And we mentioned that one goal is to try to make sense of what this notation means. Can we ever have equality? Can we ever have convergence? So we're gonna answer now in this video a simpler question. We're gonna try to answer the question of whether we can approximate such functions by objects of this type. So we're gonna first try to approximate them, then we're gonna seek some sort of equality and convergence later on. And the second thing we're doing in this video is we're gonna prove the Riemann Lebesgue lemma and we're gonna do this by proving an inequality called Bessel's inequality. So these are the things that we'll do in this video. Okay, so before we begin, maybe let's introduce an elementary simple lemma that we will need. So here's a lemma. If you have a function u that is orthogonal, so this is a more general fact, but we're going to use it for this particular inner product. So if we have u orthogonal to v, aka also known as the inner product of u and v equals to 0, then we have the so-called Pythagorean property, in the sense that the L2 norm, or the norm given by the inner product, the norm squared equals to the norm of the sum equals to the norm of u plus the norm of v squared, where here the norm of u and the norm of v squared are defined as the inner product of u with itself, and similarly for v. So we have some inner product space. So we have some inner product defined just as we have here an inner product using which we're defining a norm, and then we're saying we have this property, this Pythagorean property. Okay, so let's go ahead and quickly prove this. So here's a quick proof of this fact, or a reminder if you've seen it. So basically, the norm squared of the sum is by definition the inner product of that object with itself, which can be opened up. So if you take u with u, the inner product of u with itself is u squared, norm squared. If you take the v with the v, you get the norm of v squared. And if you take u with v, you get this, and then you get this. But then both of these guys are 0, so we get the equality that we're seeking. Okay, so this is just a simple fact here. So in particular, for us, we know that the norm of f plus g squared is equal to the norm of f squared plus the norm of g squared. Okay, so this is an important fact that we'll be using, so it's important to remember. Alright, so with that, let's go ahead and introduce trigonometric sums. So let's define trigonometric sums. And we want to define these to be, so S sub n of f is going to be defined at a point x to be the sum for all n's less than or equal to big N, like little n is ranging between minus big N and big N, of f hat of n e to the I n x. So these are called trigonometric sums. And the idea is that, again, if we're seeking some sort of relation between f and this series, then we want to begin, before we attack this harder problem, we want to begin with a simpler problem. We want to truncate this sum at n and minus n, and then study what properties these sums have. And we're gonna see that these are very good approximants of the function f. Okay, so this is what we'll see here, and this is gonna be the first theorem. So this is gonna be theorem 2 on our list for this course, and it's a theorem on best approximation. And over here, here's the claim. So let's start with an arbitrary trigonometric sum or polynomial. So let p of x be the sum over n less than or equal to n of some constant cn, some coefficients e to the I n x. So let's start with a general polynomial like this. So this is also called a trigonometric sum or a trigonometric polynomial. So maybe let's quickly put this here, trigonometric poly. Then among all such p's, among all such functions, the unique minimizer of the difference between f and p in norm is Sn. Okay, so what do we mean by that? AKA, in other words, the minimum over such p's, or the infimum, whatever, over such p's of f minus p equals this thing. So the minimum error is achieved by this trigonometric sum. Okay? In other words, if you choose the CNs to be the Fourier coefficients, then you get a good approximant, okay, in this class of approximants. Alright, so let's go ahead and prove this, and we're going to use the Pythagorean property, but the proof is going to be rather very simple. So here's the proof. So let's give a proof here. So the first observation is that for such p, if you start with any p like p of x like this, then we have the property, or we can observe that f minus p can be written as f minus SNF plus SNF minus p. In other words, I can add, so this thing is 0, but I can add 0. And the reason we want to do this is because we want to next observe that these two guys are conjugate. So let's next observe that the first element, or the first component here, is conjugate to the second one. In other words, we want to show that this is 0. But why is that? Well, to see this, let's quickly make the observation, make the following observation. So if I take f minus SNF and inner product it with e to the imx, say, if we look at this inner product, then this is by definition the inner product of f with e to the imx minus the inner product of SNF times e to the imx. And the first one is by definition the Fourier coefficient f hat at m, and the second one, by definition of Sn, we can pass the inner product to each and every one of these, like the sum of finite sum of inner product is inner product of the sum. So this becomes the sum over n less than or equal to n of f hat of n times the inner product of e to the imx. And we know by a previous theorem from last lecture that this is 0 if m is not equal to n, and it's 1 if m is equal to n. In other words, the only thing that survives from that sum is just the n equal m term. So, and the n equal m term is precisely f hat of m times 1, and thus this is 0. So for every so this was proven for every m less than or equal to n, we have this property, right? So in particular, we know that it holds for this. Let's call this star. Thus, star follows since SNF minus P, say of x, is basically f hat of n minus Cn, e to the I n x for n less than or equal to n. So this is by definition of S and P. We have this, and thus we can also pass the inner product. So the inner product of each of these, of this with each of these, is 0. So we can interchange here and pass to the inner objects, like interchange inner product and sums, because this is finite, and we get a star. Okay, so star follows like this. And at this point, we're gonna invoke the lemma that we proved, which is over here. So now we have two quote-unquote objects or vectors that are orthogonal to each others. So we have this Pythagorean property. So if we call this u and this v, then u is orthogonal to v because the inner product is 0, and thus f minus p, which is u plus v, has the property that its norm squared equals the norm of u squared plus the norm of v squared, which is the norm of the first object, f minus snf squared, plus the norm of the second object, snf minus p squared. Okay? And this finishes the proof, because if I'm trying to minimize, we're trying to make the error between f and p as small as possible by making the right choice of p, then we notice that this is independent of p, and to make this as small as possible, we can simply choose p to be snf. So this is the smallest when, when p is equal to, because it's bigger than or equal to 0, so it's the smallest when it is 0, when p is equal to snf, right? So this means that p must be snf, and this finishes the proof that we wanted. Okay, so we just literally proved that the object p that minimizes this error is exactly this. Okay, so in this sense, this object, this trigonometric sum with these particular coefficients, the Fourier coefficients, is a best approximant in this particular setting. Okay. Alright, so with this, we can now prove our next result, which is gonna give us the Riemann Lebesgue Lemma as a corollary. So let's go ahead and prove Bessel's inequality. So here's another theorem. So this is theorem 3, and it is Bessel's inequality. Okay, so what do we want to prove here? We want to show that for any L2 periodic 2π periodic function, f, in other words, the integral of f squared over minus pi is finite, and it is 2π periodic. So for any such function, and notice that it's enough to see that since f is bounded, if it's enough to assume Riemann integrability, because if f is bounded, then this is immediately true. But anyways, so for any such function, we have the sum of these coefficients squared as n runs over z, like from minus infinity to infinity, this is less than or equal the norm of the function. Okay, so let's see how to prove that. So here's a proof. So let's begin with the proof like this. So we're going to be using the orthogonality property again and again to be able to get what we want. But the idea is this. Recall again. We have that e to the I n x, inner product e to the I m x. This is 1 if n is m and 0 otherwise. And we're going to use this to compute the inner product of, the norm of this object. So let's first try to see what's the norm of this object here. So the norm of this object is by definition the inner product of the object with itself. So recalling the definition of SNF, this is exactly the sum of n less than or equal to n of f hat of n e to the I n x. So this is what s n of f is, and again with itself, right? So maybe let's use an m here just to avoid confusion. So this is f hat of m e to the I m x. This is an m. Then this inner product, if you open it up, like these finite sums, if you expand and you combine the kth term here with the lth term here, and you write this as a sum, you can easily see that this is the sum of n as m and n run over all values less than or equal to n of f hat of n times f hat of m, like the nth term here multiplies the mth term here, and then we have the inner product of the nth term with the mth term, right? So if you open up these sums, you expand them, this is what you end up with. However, again, this survives only when n is equal to m and it's 0 otherwise. So this is gonna survive only when n is equal to m. So we obtain only one sum with n equal to m, and then this is gonna be multiplied by 1. This becomes an n. Actually, let me just make one correction here. When you inner product, by definition of inner product, there's a conjugate here that you need to account for. So complex conjugate. So let's just account for that since we're working in a full generality. So there's a complex conjugate here, and thus this becomes complex conjugated, which means this is the sum of n less than or equal to n of f hat of n absolute value squared, which means we just showed that this thing equals this thing. So let me write it here. So this is SNF norm squared equals this. So this is the first observation. With this observation, we can pretty much finish the proof, and let's see why. So now recall from the previous proof. So from the previous proof, we've shown that the f minus SNF, when you inner product this with e to the I m x, this is 0 for m less than or equal to n. So this is literally what we proved in the previous proof. In particular, f minus SNF is orthogonal to e to the I m x. So this we know, and thus again f minus SNF is orthogonal to SNF, which equals the sum of f hat of n e to the I n x, right? So since this is a finite sum, if I inner product this with this, I can simply take this and inner product it individually with these and pull up a constant, and each of these is 0, and hence the inner product of this with this is 0. So they're orthogonal. So in particular, I can also apply Pythagoras theorem, so thus, or lemma, thus by Pythagoras, we know, like, if this is the u and this is the v, then their sum, the L2 norm of f, which is squared, which is the L2 norm of f minus SNF plus SNF, this thing, since this is the u and this is the v and they're orthogonal, this is the norm of the first squared plus the norm of the second squared. But then what does this mean? Well, this means that since we have this equality here, so first of all, this thing is bigger than or equal to 0, so this thing is bigger than or equal, so this thing is bigger than or equal, this norm squared, which we have shown to equal this guy. So it equals the sum over n less than or equal to n of f hat of n squared. But this holds for every n, so I can send n to infinity after recognizing the inequality between these two, and get that the sum of n between minus infinity and infinity of f hat of n squared is less than or equal to this norm squared. Okay, so this finishes the proof of Bessel's inequality, and we are now ready to give a very short proof of the Riemann Lebesgue lemma. So let's go ahead and state and prove that. So the Riemann Lebesgue lemma says if f is integrable on minus pi, can also think of a 2π periodic function, but in particular, like it's Riemann integrable, so in particular it's bounded on this compact interval, then we have the nth Fourier coefficient tends to 0 as n tends to infinity. This is a very important lemma that we will see. It has numerous applications. So let's go ahead and give a quick proof of it. So it's literally one line now. So as a proof, if f is bounded, if it's also integrable, Riemann integrable, then f is in L2 of minus pi, meaning the integral from minus pi of f squared is finite. And why is that? Well, it's because it's bounded. So you can bound this by some constant, say m, and then you're left with an integral of 1 between minus pi and pi, which is m times pi plus pi, which is finite. So it's square integrable. It's L2. It's in L2, and thus we can invoke Bessel's inequality. So we can invoke this inequality, thus by Bessel's inequality. So here I'm writing out the details for completeness, but the proof is clear. So this is the integral. The Bessel tells us that the sum of these squared is less than or equal to the L2 norm squared, right? But we know the L2 norm is finite because this is finite. So this is finite. So this series over here is finite, but its terms are non-negative, bigger than or equal to 0. And then by the nth term test, the nth coefficient must go to 0 as n tends to infinity in absolute value. So we could have put absolute value here, like it could go to plus or minus infinity. Okay, so this finishes the proof of the Riemann Lebesgue Lemma. And we will next see some applications of this lemma, and for that, stay tuned. Thanks for watching.